recording?
Or,
Okay.
Never mind. I didn't know if we should mute because, like, we're eating. Should we always mute? Oh, okay.
Your preference, whatever you want. Okay, so yeah, so active learning, I think, had a big boost when Amazon Mechanical Turk came out. And there's actually quite a large number of different machine learning applications I know of that use Mechanical Turk. You can just use Mechanical Turk to try to do normal supervised learning. And I guess from a theory perspective, the way you think about that is you have unlabeled data, you draw a random subset of the unlabeled data, and you ask for the label on that random subset. Right? That would be the standard notion of what supervised learning should look like if you're trying to label things. Now, often you have the opportunity available to kind of interactively choose which examples you want to label, and that can be powerful potentially. It can also be very dangerous potentially. You can end up reaching an unfounded state where you cannot even find the solution. And I think the thing to think back to is all the discussion about reinforcement learning and contextual bandits. If you get the wrong data, then you can't ever find the right solution, and so potentially you could make things not work. Okay, so you want to use your unlabeled data somehow in order to improve your performance. You have some unlabeled points. Some people just try to do straight up unlabeled, unsupervised learning. That's very difficult to make work in a useful way. Occasionally it can be useful. You can do supervised learning, where you pick a random subset and you label them. Or maybe you want to kind of interactively choose which examples to label, and that would be called active learning. Or I guess there's another version where you already have labels, but you also have unlabeled data, and you're trying to kind of learn a good predictor for the labeled data in the presence of the unlabeled data, which kind of adds some advice, right? That'd be called semi-supervised learning. Okay, so we're going to be talking about active learning here. And now the question is, how powerful is interaction? So maybe repeatedly, you observe some unlabeled example X, and then you ask for a label, either yes or no. And if you do ask for a label, then you use that label Y to update the state of your learning algorithm. So you want to kind of simultaneously optimize the quality of the learned classifier and minimize the number of labels that are requested. So there's just kind of a two criteria situation here, where you want to have good prediction performance, but you want to minimize the cost to the oracle in achieving it.
And then how do you trade off between the two goals? Like, you can just pick.
That's not easily answered, actually. There's no, see, the difficulty is you don't know in advance. There isn't a good knob to turn to optimize some Pareto frontier, because you're in a situation where you only observe the labels that you actually ask for. And so it's very difficult to say, oh, if I had asked for more labels, then I would have gotten better performance. It may not even be true sometimes, but you certainly can't observe that from the data that you have. And that makes it a more delicate process than you might otherwise hope for.
So, step one, you're not going to observe X again? Or you might, or with IID?
So here I'm thinking about a streaming setting.
Mm-hmm.
There's also pool-based active learning, which we'll talk about in a moment. Now, pool-based active learning actually is one of those things which is pretty great in simulation and not necessarily so great in practice.
That's what people do it most of the time. At least
some people try to do it that way.
in NLP, that's what like the common thing.
Okay, let's talk about this a minute. So let's talk about pool-based active learning. So you start with a pool of unlabeled data. You pick up a few points, you get some labels, and then maybe you fit a classifier, and then you query the unlabeled point that is closest to the boundary. This would be a common kind of approach. Or maybe this is the most uncertain or most likely to decrease overall uncertainty. It's several different criteria for how people choose to label things. But the point here is that what you choose to label is essentially deterministic. And that should be a little bit scary in this case, because it means that you have a very biased labeling process, and that can kind of go wrong. So I think the question is the structure of the boundary around where you chose to label the right place to be seeking labels? And it's certainly very possible to create problems where the answer is no, definitely not. And empirically, there's actually been some observations that this can go quite wrong. Okay, so here's an example, a data set. So I'm showing you the true distribution. Red is one label, green is another label. There's only one feature, which is the value on the x-axis. And let's say we're just using a threshold classifier. So it'll start out saying red, and then at some point you transition and you say green, right? So if you select 5 points at random, and then you label them, with high probability those 5 points will be either from the red 45% or the green 45%, right? So then you'll have some labels, and you'll go, all right, so I'll just split in the middle. So you have this middle 5% of the data, and then you're going to query for examples in that middle 5% of the data, right? Because that's nearest to the boundary, right? So you query for the points that are nearest to the boundary, and you pin down the boundary, and then unbeknownst to you, because you never queried it, there's this 5% pool to the side of green points. Okay, so that means that your error rate is going to be 5%, which you cannot measure because you never labeled there. And furthermore, you can do better than 5%. If you choose to do the threshold right at the 45% boundary, you'd end up having a 2.5% error rate. Right? So this is, I would say this is not consistent. So you would like a active learning process, which for any given set of classifiers will eventually choose the best classifier in the set. That's a property that supervised learning has. If you're doing supervised learning and you choose the minimum error rate classifier in your set of classifiers, and it's not some sort of crazy super non-parametric thing, you will eventually converge to the minimum error classifier. Yeah?
So it seems a lot depends on, in streaming case, how the points are given to us. Like, do we make an assumption that the points come like uniformly at random? Because you can adversarially give those points.
Yeah.
Really mess up.
Yeah. So in the streaming case, we're typically thinking about things coming uniformly at random, or maybe not uniformly isn't the right word, but IID. So the sum distribution D, which generates the points in the labels. A random draw happens. We see the point, and then we choose whether or not to observe the label. Okay, so the claim is that there is a failure mode for pool-based active learning. And I think what people observe in practice is that sometimes this failure mode actually happens, sometimes it does not, but it's definitely there, and it is a real concern. So what I'm going to be talking about mostly is how to create active learning algorithms that do not have this failure mode, which will work in the presence of arbitrary noise and will eventually converge to giving you the best possible answer. Okay, so there's kind of three pieces. One piece, we're going to talk about how to use importance weighting So we're familiar with importance weighting from contextual bandits. In the other piece, we'll talk about how to deal with rare classes. And in the third piece, we'll talk about how to deal with cost-sensitive multi-class classification. Are there questions about this failure mode? Okay, so let's think about importance-weighted active learning. So I would call this the eyewall algorithm. You start out with no labels. You run through your unlabeled examples. You receive some unlabeled example. You choose some probability of labeling it. So that probability will be P. And then with probability P, you get the label Y. And then you add X, Y, and with an importance weighted 1 over P to your data set. Okay, and then we just, we let our hypothesis be whatever we learn on that data set.
So this learner, isn't it, it has to somehow use the weights, doesn't it?
Yeah. So I'm imagining this is an importance-weighted learning algorithm, which means that it kind of weights the individual samples according to whatever the importance weight is. And so it'll minimize the importance-weighted error rate. Okay, and now the claim is that if you use essentially any reasonable choice of P in learn, so for all methods choosing a P greater than 0, if learn minimizes the error rate, the importance weighted error rate, then the algorithm is consistent. So that failure mode that I just showed you goes away, at least asymptotically. You will converge to the right answer.
What's the intuition between 1 over P?
So the intuition for the 1 over P is similar to the intuition in contextual methods, where we also use a 1 over P. So if you choose an example rarely, then you want to value its error or success to a greater extent than otherwise.
So here the P in each round we can have a different P, right?
Yeah, every P can be different. And in fact, you would want it to be different or else it would not be very interesting. Essentially, if you chose the same P every round, it would essentially be equivalent to kind of a supervised learning approach.
Right.
So this,
So how do we choose P, I guess?
Yeah, so that's what we're going to spend some more time on. So the basic claim is that you can do just about anything as long as P doesn't go to 0, or at least doesn't go to 0 too fast. But there are some approaches which maybe work better than others. And that's what the next part is about. Okay, so how should P be chosen? So let's define some things. So you have the importance weighted error rate. Right? So this is the same as the normal error rate, except that now we importance weight according to I. So that's the empirical importance weighted error rate. So we have, if we go back, we see we have some hypothesis H. So I'm going to define an H prime, which is the minimum error rate hypothesis choosing the other label. So I'm going to think about, I have a set of classifiers. Maybe I have a decision tree, which splits on the first attribute for the first classifier, and I have a decision tree which splits on the second attribute as a second classifier. So there's many different possible classifiers in my set of classifiers, and I want the one which constrained to predict differently from H minimizes the error rate, right? Okay, so the difference in these error rates is delta. And because H is learned without any constraints, H prime has a constraint, so the error rate of H prime will always be at least as large as the error rate of H, right? Okay, so that means delta is positive. That's good to know. Okay, so now if delta is too small, we're going to let p equal 1. So we query with probability 1. And otherwise, we end up querying with a probability which is like log k over delta squared k. So k is the number of samples here. All right, so the exact details are driven by a theorem, but maybe it's important to kind of look at things at a higher level. So delta is the error rate difference. So if delta is like a constant, then p, well, okay, if delta is like a constant, then eventually the square root of log k over k will be larger than that constant, and you'll query with probability 1. So you want a delta which is actually growing to think about when you will not query. But it doesn't have to grow very fast because you're kind of comparing delta squared to k. So if you look at the denominator, you see there's a delta squared times k. So if delta is like 1 over root k, then the denominator becomes order 1. Okay.
What is K? Sorry, what is K?
K is the number of samples.
Okay.
Maybe I should have used T here, but it's K. So when delta is substantially larger than 1 over root k, you end up not querying. Okay, so you can prove a theorem about this. You can say with high probability, the I-wall reduction has a similar error rate to supervised learning on k points. So this is addressing the trade-off point, the trade-off question. So when we prove these theorems, often what we end up doing is we say, okay, we have the performance that we get if we do supervised learning. I would like to get the same performance up to some sort of constant loss and convergence, but I would like to do it with fewer observations. So this is one way to do the trade-off. It's not clear this is the best way to do the trade-off, but it's what we know how to analyze right now. You can also prove that the number of samples can be substantially less than k as long as something called the disagreement coefficient is small. And I'll discuss what that is in a moment. So are there questions about this? The key issue is just how much extra error rate would predicting the other way imply? And if that is large, then the probability of sampling will be small. So that means that once your classifier kind of settles on an individual label, it will just stick with that. Okay, so let's discuss the disagreement coefficient for a minute. So disagreement coefficient is a way to characterize kind of where active learning can help you. And it's a little bit tricky because disagreement coefficient is dependent upon both the set of classifiers and the distribution that you're dealing with. Okay, so let's pick an epsilon. Epsilon is going to be some value between 0 and 1. Let's think about some hypothesis h. If the error rate is of h is less than epsilon, Okay, so and the question is, do we want to actually query or not? So you have your H star, which is your best classifier. You don't know it in advance. But the question is, does there exist another classifier which is nearby, in the sense that it has a small error rate, but it predicts the other way on that particular X? So if that exists, then there's a disagreement within kind of an implicit version space, which is the set of all classifiers which are within epsilon error rate. Okay, so the disagreement coefficient is sort of the worst case over any given epsilon of this quantity when you kind of divide by epsilon. So the disagreement coefficient is the probability that an X has a disagreement within a region epsilon, all that divided by epsilon. So the division by epsilon is, so as epsilon gets smaller and smaller, the probability of disagreement gets smaller and smaller and smaller. So you need to divide by epsilon so that you actually get something which doesn't go to zero, right? Okay, so the thing to have in mind is you have the best classifier, you have all the nearby classifiers, you have the set of points that the nearby classifiers disagree on the best classifier with, and then as you vary your notion of nearby, you want to know how that set expands and contracts.
So dividing by epsilon, would we have divided by something else, like epsilon squared? Like I'm thinking, like if we think of hypothesis space as like R2, then if epsilon is like radius, so it depends on dimension.
Yeah.
Like whether you want to divide by epsilon squared or cubed or.
Yeah. So epsilon turns out to be relatively natural. It's not. There's nothing saying that this is absolutely the right thing to do. It just, you get reasonable looking formulas out for various choices when you do it. You could imagine doing something else, and in particular, so let me go back here. This analysis here is actually kind of pessimistic because it assumes that all of the errors are kind of within a small epsilon region. So in some sense, you would prefer to have a more refined notion than the disagreement coefficient, because the disagreement coefficient doesn't take into account where the errors happen, where necessary errors are in your classifier set. Let me rephrase that. So this result holds when all of the reason that there's a minimum error rate greater than 0 is near the disagreement set for a small epsilon around H star. Right. So that's a pretty pessimistic viewpoint. In particular, it may easily be the case that there are kind of outliers that create errors, and as you do active learning, you'll just cease to query in the region of the outliers. And then the results that you'll observe would actually be better than what's getting proved here. Okay, so let's give some examples. Suppose you're just doing thresholds on a line. So below the threshold, the prediction is -1, above it's +1. Then theta is 2. Suppose you're doing linear separators. So you're just doing, you're just splitting the distribution. Let's pretend that the features on X are uniform over a sphere. And so all of your features are sphered, which is actually a common transformation you do before you feed data into a learning algorithm. And now you're just trying to learn a linear separator, which splits one class from another. The disagreement coefficient is about square root of the number of dimensions. So that square root of the number of dimensions is actually a little bit tricky. You have to, so think about a sphere. Think about a hyperplane cutting the sphere. So think about the orthogonal to that hyperplane. So as you vary the orthogonal, you vary around nearby spheres. And now the question is sort of how much of the sphere gets swept out by the disagreeing nearby hypotheses. That ends up being something like a root D fraction of things. Or whatever root D fraction. So you can talk about more complex things. I don't know. I mean, there are various special cases where people have proved disagreement coefficients. I think in practice, you may not even know for any individual problem that you're trying to apply active learning to, because your hypothesis space will not be one of these idealized hypothesis spaces. But nevertheless, the concept, I think, is kind of useful because it gives you a way to think about how to improve on supervised learning. Okay, so here are some experiments where we played around with using decision trees to do passive versus active learning. So in the passive learning, there's some number of labels chosen at random from the data set, which is used to train. In active learning, you're running along, you're using this algorithm for choosing whether or not to label, and you're seeing whatever performance you get on the test set. Right? So we have the test error here. Okay, so what do you see? Okay, so first of all, I should tell you that all of these are sort of active learning by simulation results. So you have a large supervised data set, and now you run through the supervised data set, and you ask to label or not, you ask to label or not over and over again, and then we're recording the test error performance as a function of the number of labels. Okay, so what this means is that typically the active learner cannot request as many labels as the supervised learner because it runs out of data set to request from. And we don't want to loop through things because then you can end up getting a biased report. Okay, so what you see is that the performance sometimes matches supervised learning and sometimes is a good bit better. Sometimes it's even better when you get to a relatively large number of samples. So I think the theory does not explain this, but it's a common observation that when you do active learning, you may actually end up getting better performance than if you had done supervised learning. And now the question is, why is that?
So what's the supervised learning here? You just sample randomly a subset?
Yeah.
Mm-hmm.
So why would you actually do better than if you're doing supervised learning?
On the x-axis, number of labels queried.
Yeah.
Does that mean like the active learner was showed these number of queries or the ones that he actually queried?
Actually queried. So the number of unlabeled points is what's that?
And then for the supervised case, it would mean that all the labels were shown for the query.
Yeah, so in supervised, everything is queried. In active learning, only the number up to that point are queried. Right, so let's look at the KDD Cup 99 data set, right? So about, I don't know, 750 examples are queried by the end, by the active learner, while the supervised learner queries 5,000.
Why did active learner stop?
It's because you're running through the data.
Mm-hmm.
We're imagining the data was drawn IID and then labeled. So we want to be able to simulate what would happen if you were working with an actual stream. Mm-hmm. So you run through the data one at a time, you make a decision, you live with the decision, and then you run out of data at some point. Okay, so why does active learning actually do better than supervised learning? Edith? Ashwin. Wrong one.
Because it didn't query for the noisy labels, like the noise in the data. So it didn't query
didn't have to learn.
Yeah, I think there's something along the lines of what you're saying. So there may be a lot of noise around the boundary, but that noise is not really that harmful to your prediction performance. What's harmful in many cases is when you have noise far from the boundary. And although we have an agnostic active learning algorithm, it tends to query less far from the boundary. And so it tends to miss noise far from the boundary. And then that, I think, does not disturb the overall optimization as much as it would be in a supervised case. You were saying something?
So in the cases of the KDD cups,
Yeah.
it actually sees all the data because the plot line for the active learner continues all the way, like 600.
No, this is a close-up. No, look at the number of labels queried. You're talking about the on the bottom.
Yeah.
It's just a close-up of what it looks like from 0 to 700.
Okay.
So, like in that case, again, I'm so confused a little bit. Like if we look at the 600 on the x-axis, if we look at 600,
Yeah.
and then go up, and like, what does the red curve mean? Like, how many labels were in the supervised case? 600 were shown.
Yeah. So in supervised case, the 600 mark would be where you had 600 examples all labeled.
Okay.
Well, in the active learning case, the 600 line would be the point at which you had 600 labeled examples, which would be after you'd seen many more unlabeled examples. Okay. Now, it's kind of a question about how you implement this efficiently, right? Because there's this whole thing about finding a hypothesis that's constrained to predict the other way, but otherwise minimizing the error rate. And so that's it. Maybe on a decision tree that's relatively straightforward, but you'd like a manner for doing this which is very efficient so that you can apply it to large-scale data sets. So I want to tell you about an approach to do this for large-scale data sets. And it's a little bit tricky, but it turns out there's a transformation which is very powerful. Okay, so h of x is the output of your learning algorithm. H prime of x is the output of your learning algorithm when it's constrained to predict the other way. So what we want to do is we want to say h prime of x differs from h of x by one example with an unknown importance weight. Okay, so in particular, okay, so delta was the difference in the error rates. See, I switched back to using t here. So t was k. T is your number of samples. So t delta is sort of the amount of extra error that you encounter. And now the claim is that if you take your data set S and you plug in the opposite label from h of x, and you plug in t delta plus a tiny bit because it's technicalities, then the learning algorithm will in fact output h prime of x. Okay, so what does this mean? This means that the difference between h of x and h prime of x is one example with the same features as the present, the opposite label as our predicted label, and an unknown importance weight. And that means that we could search for this importance weight, or we could do something else. There's various ways we could try to figure out what that importance weight is, but the only thing we need to figure out in order to run our algorithm is essentially the importance weight. That is the relevant bit of information that we need. So how much importance weight is required in the opposite label to cause you to predict the other way on this example? Okay, so inside of EW, you can actually query the base learner, and you can ask it directly how sensitive is the prediction to an example with a particular label. And then given the prediction and the sensitivity, you can just estimate directly what that critical importance weight would be.
So T delta here is one symbol. It's not T times delta.
It's T times delta.
T times delta. And T is the
T is the number of samples. So
That's
T
what it
times
is
delta
called.
is really like the sum of the errors between H prime and H. So let's go back to
H prime and H, or T is the number of samples that.
here. So delta is defined here.
Mm-hmm.
So it's a difference in the empirical error rates.
Mm-hmm.
And T is really K. So this is like the importance weighted difference in error, total error, not normalized error.
Okay.
Okay, so all we need to do is find that critical importance weight. And if you can examine your learning algorithm and estimate how many samples are required of the opposite label in order to cause your prediction to change, you can get at the importance weight directly. Okay? So you don't even need to, it's not quite a black box reduction. You're asking a little bit more information from the Oracle. You're asking it how sensitive its predictions are to updates. But that turns out to be very feasible in linear land, and it's somewhat feasible even in neural network land.
It's very hard to estimate this.
Why do you think it's hard?
It's hard to estimate like the number of, I mean, especially in neural networks, the number of gradient updates you need.
So it becomes hard when you're far from the boundary.
Mm-hmm.
But far from the boundary is actually where it's least important to estimate things well.
Yeah.
So when you're near the boundary, things you can do kind of a linear approximation through the neural network,
Mm-hmm.
and then you can make some sort of estimate.
Yeah, and we also have to take into account the learner. So if you have an adaptive gradient learner,
Yeah.
that's
So VW uses an adaptive gradient learner, and it does this kind of thing.
Mhm.
It's not trivial. I mean, there's an extra function called an interface, basically, to estimate the sensitivity. But it can be done, and so you can use your learning algorithm, the one that you otherwise normally use, to get at active learning. Okay, so you can, this is actually in VW. I didn't quite figure I'd have time for a demo, but there's a protocol, there's a little helper function, you can active interactor, you can interact with it. You feed in an unlabeled example, it chooses to query or not. You choose to produce the label, and then maybe later on you send in another unlabeled data and it says no query, and it goes back and forth. You can also do sort of an active simulation mode, which is what was used to generate those experimental results. Okay, so in general, I think there's a number of different nice properties here. This is I think, this is not the empirically optimal algorithm, or this is not the theoretically optimal algorithm, but I think this is essentially a near empirically optimal algorithm if you are worried about that failure mode where you just kind of go off track as you get more and more data. If you want to be able to converge, importance weighted active learning seems like a pretty good approach. So it's always consistent, so you have kind of a strong safety guarantee. And that means that you're free to kind of fool around with the probabilities if you want to, and if it might make sense in your individual problem. It's efficient, so it's kind of label efficient. It's unlabeled data efficient. It's also computationally efficient as long as you can make that estimate of the importance weight efficiently. It's compatible with lots of different things. So you can do online algorithms. You can do different kinds of loss functions. You can do different kinds of supervised learning algorithms. You can take a data set which is trained on one algorithm. So you train your active learning algorithm with one representation, like decision trees. And you could go and you could even apply this to a linear representation or a neural network representation. And that would make sense, and your estimates would still be good. It's just that your performance may not, how can I say this? So there's a danger with active learning that you get locked into a particular learning algorithm, because the learning algorithm is being applied as the data set is being collected. And so you end up collecting the right data set for that learning algorithm. So that could be a lock-in that you don't want. You may want to have the freedom to be able to switch to a different learning algorithm at some point in the future. So using these importance weighting approaches, you can do that. And what will happen is just the amount of data that you have for that learning algorithm will kind of effectively be smaller than it would be if you had been using that learning algorithm from the beginning in order to drive the active learning process. And so you could compensate for that and to make a comparison between, you know, whatever learning algorithm was used to gather the data and whichever one you want to consider switching to. Okay, so this is importance weighted active learning. And it also works, right? So now let's talk about, are there any questions about importance weighted active learning? Okay, so now let's talk about rare classes. Rare classes are kind of a fun subject. So let's think about applying the algorithm we just talked about when you have a rare class. So here we have green and red. Green is the common class, red is the rare class. And maybe we want to, instead of using threshold classifiers, maybe we want to use just a little bump classifier, right? So we want to classify with one small interval, which is positive. How many labeled examples are required in order to learn to do better than the always green predictor? What's that?
Constant of one.
You need one.
Constant. Like,
so how would you do that?
I mean, like if your hypothesis class is one bump, then you can fix the bump to be like the mean of, like, oh, so you have another parameter of the breadth of the bump?
Yeah, it's like a two parameter. You could think of it as the beginning and the end of the bump, but either way.
You can use some like statistics. So like just I'm not sure if it's the right direction, but like if you have one example, then you would probably fit it to just like a, you know. Okay, if you had n examples of the red class, then you would probably want to fit it like some 95% confidence interval of that red class, something like that. Right?
So if you think back, let's think back to the eyewall algorithm, right? So we're running through, we get a uniform random unlabeled example. Do we want to label it or not? How many times do we have to keep asking for a label before we find something that doesn't say green?
It's like a binary search.
It would be binary search. It's not binary search at the beginning though, because we have no red examples.
Yeah.
And so you're running through, you get an unlabeled example, you know nothing, so you say label it. It's green. And then you say green, 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 green.
Yeah.
You say green many times. And now eventually you'll hit that little region with a red, and then you have a red. At that point, you can switch over to doing a binary search because you know there's a red here. Okay, so there must be some boundary to the greens here and some boundary on that side. But until you find that initial red, it's kind of a needle in the haystack problem with no magnet. Right? Okay, so there's a paper by Josh Attenberg and Foster Provost a while ago saying that search can be very powerful in the situation. So if you allow people to search for that one red example and put it into their data set, then that can become a very powerful way to achieve a small error rate quickly.
So it's necessary that it's people?
What's that?
So it has to be people. That was
I don't know if it has to be people, but any mechanism for searching could potentially help you get around this. Now, there's kind of a question, though, about when does this help or hurt. Right. So the problem with search is that you're creating a biased data set. Right. And biased data sets can be bad in many cases. So now the question is, what can you do about this? Or how do you even think about how to use this effectively? Yeah.
So by search, you mean like just like going out in the world and looking for this like rare example?
Yeah. So you could create, I think a common example of this would be something where maybe you want to make a web page predictor. Is this web page about fire engines or not? Right? So there's not many web pages that are about fire engines. If you sample uniform randomly, it'll take you a very long time to find one. But you could probably do some sort of keyword search on a search engine and find something pretty quick. And then throw that into your data set.
But if you're optimizing the search engine, it's kind of like garbage in, garbage out.
Yeah, potentially.
Yeah.
So there's a difference, though, in that if you're trying to create a classifier of fire engine or not, it's solving a somewhat different task than a search engine. Search engine is just so you're getting some leverage from something which is related, but which is not exactly the same.
No, I understand. I'm just there is this. What if we do it on a search engine? What if we want to optimize our search engine this way? Then querying the search engine is a bit, I don't know, it's a bit biased maybe.
Oh yeah. So bias is definitely a danger with any search approach here. There is an observation, though, and we can't dispute it, that empirically this can be a very powerful thing to do. So we want to come up with a way to safely use search, and we want a way to understand when and why search can be powerful.
You can use some randomized search policy, like the probability, which is very good point. Use
To inject noise, basically.
I was thinking about randomly searching in the same sense that we kind of randomly queried previously.
So we define a distribution.
Yeah, you could try to do that. It seems like the importance weights would become dramatically large in realistic applications if you do this. So I don't see a direct way to take advantage of that. Yeah?
So like in this green and red example, how does search work? Isn't it like very similar to like going through all the examples and finding whether or not it's green or red? And then in that case, we're doing just what we would have done.
So I think the way that search works is kind of very problem dependent. So it's hard to say. Maybe there's some pre-existing index that can be used to search more efficiently than an enumerative style. Or maybe you're making a photograph, a penguin detector, and you happen to know your friend who has some photos of penguins, and you go and you talk to them, and you say, hey, can I have your photos of penguins? I'd like to put them into my penguin detector. Right? So there's a lot of ad hoc ways that search can be fulfilled as an oracle. It's very problem dependent exactly how that happens.
Like you might have a friend who has this red example and ask him to get the red.
Yeah, potentially. Or maybe you're looking for pictures of fire engines, so you walk over to your local fire station and you take a picture.
Brooklyn fire engine.
Yeah. Okay, so if you have search, then suddenly it becomes a binary search problem, right? Once you have that one red example, then it becomes just find the boundary of the red area, and you can narrow in on things, and yeah, it works. So potentially you could get an exponential improvement in your label complexity. So that,
you mean label complexity? So like
the number of labeled examples needed in order to solve the problem. Right. Okay. Okay, so now we want to think about why search is powerful, why it's useful. So let's think about counterexamples for a minute. So suppose that we're thinking about, so we have one labeled point, one green point, and now I say, hey, I want a counterexample to this green point. or a counterexample to the hypotheses that are consistent with this green point. So you have the set of all of your predictors. You have the set which is consistent with the observation you've made so far. So I've tried to show this here, but it's a little bit confusing because there's many different classifiers which are consistent. So you could have one which says, oh, everything to the left of the point is red, or it could be a much smaller portion to the left, which is red. Right, but the thing that you're relatively sure about, if we structure things the right way, is that everything to the right is a green. Just because of the way the set of classifiers is constructed. It may not even be true here. Okay, yeah. Anyways, you can ask, what is a counterexample to a learned hypothesis? So the hypothesis that I put down here is zero error rate. The hypothesis says it's red to the left and it's green to the right. So I can say, what is a counterexample? And you can come back with a counterexample and you can say, oh, there's a counterexample, right? And you can say, oh, here's another counterexample, and then here's a counterexample, and so forth. So if you think about search as a mechanism for creating counterexamples to a learned hypothesis, it just doesn't work. It could take it could be that all the counterexamples you get are right. They don't really change things very much, and that's disturbing. So search is not just a mechanism for creating counterexamples, because the counterexamples may not actually shift your learning algorithm in any significant way. Okay, so the trick here is that we're going to shift from thinking about counterexamples to a classifier, to thinking about counterexamples to a version space. Okay, so in particular, we're gonna create a set of classifiers which are simple, and then more complex, and then more complex, and then more complex. So maybe our first set of classifiers is always green or always red, right? And then we see one unlabeled example, we ask for the label, it's green, and then we say, this is the all green classifier. And then you say, please find a counterexample to this, to the search oracle. And it goes, here's the counterexample. Right? And now the next more complex set of classifiers will be maybe something which has red to the, it'll be a threshold function, right? So we'll have red to the left, and then we'll have green. And then this is one example classifier, which is from that space. So once you have a counterexample to the set of classifiers that you're working with, you can boot up to the next more complex set of classifiers. And if you do this right, it turns out that this actually works. So if you search for a version space counterexample, a counterexample to all of the plausible choices that you currently have or considering for active learning, then that can reduce the number of labels required exponentially. So I don't want to go into the details, but this is kind of the essence of things. We have simple and more complex, more complex, more complex sets of classifiers. You start simple. When search proves you wrong with that simplicity, you move up to the next most complex thing. And you just keep doing that. And that process of moving from simple to complex ends up creating the points which allows you to do the binary search that Ashwin wanted to do. Okay, so that's rare classes. And the last thing I want to talk about is cost-sensitive classification. So we've discussed cost-sensitive classification multiple times in this here. So just as a reminder, we're thinking about the situation where we have a number of classes and there's a cost associated with each class. So our goal is to minimize the expected costs of the chosen class. So the form of the predictor is the same as multi-class, just choosing one of k classes. But instead of saying a 0-1 loss, we have a cost-sensitive loss. Again, this is as we've seen, this is a more powerful primitive than multi-class. There's a lot of situations where this can express partial credit, and you would like to be able to do active learning in that kind of situation. Okay, so one question that comes up immediately is, should you be querying per example or per cost? And so if you, say again?
I was just going to ask, what's the incentive for doing it per example?
Well, previously, I guess, when we were doing active learning, we would query for the entire label for that example. So that would mean per example. So if we ask for the label, a full label, that would be a kind of a per example method of, so you get the entire cost vector. On the other hand, maybe you don't need all the costs. Maybe you can get by with only a few of the costs.
So is it that when we query for particular X and a particular Y, like we just get a banded people? Like, do we just get whether this class was the true class or not, or do we get the entire?
So if our cost structure mimicked multi-class, which means that we have a cost of 1 for every class except for one class which has cost 0, and we only queried for one cost, that would be what would happen.
Yeah.
So that would be very close to the bandit setting, right? The architectural bandit setting.
Right.
It's better if we can do for cost, I guess. Because then we need even less information.
Yeah. I guess our feeling in thinking about this was there is kind of a cost associated with every individual example that you want to query on, because somebody would have to look at that example and think about that example for a minute. And then there's an additional cost kind of per cost that you query. So what we analyzed was kind of a linear combination of the two.
So where does this actually occur?
Where does what occur?
Like this conflict that you can acquire only part of the label has the higher cost.
I think you can, so for active learning, we're imagining that you can acquire all of the label if you want to.
Mm-hmm.
It's just that you may not want to because that's expensive, in the same sense that getting a large label data set is expensive.
Yeah, but when you're saying, so given a sample that I ask a label for,
yeah,
the two alternatives is ask the annotator to give me the entire label, the
yeah,
entire parse tree, for example.
Yeah.
Or I ask him to give me this part of the parse tree.
Yeah.
But in parse trees, for example, this is kind of very artificial scenario because I can't ask for part of the parse tree.
Yeah.
The annotator will build the entire parse tree.
Yeah.
So I just wonder, where does this happen? Because when you have a lot of decisions, they often depend on one another.
So I'm not showing it here, but we're actually going to figure out how to use this algorithm in the context of learning to search algorithms,
mm-hmm.
where you're essentially filling in costs.
Uh-huh.
And then instead of filling in all the costs, maybe we can just fill in a subset of the costs. And that's it's a computational improvement.
So the learning algorithm is faster and less complex, basically?
It's faster.
Okay. But in those cases, you have a labeled data set. So it's not an active learning scenario. You're just kind of importing these ideas to
optimize the process of doing learning to search.
Cool. Okay.
Right.
That makes sense. Nice.
Okay, so let's think about a set of costs. So we have an individual example, and we have a set of different predictors of costs which have not yet been ruled out. So we're thinking about essentially a version space. So for every cost given this example, or for every action, or sorry, for every class label given this action, given the features of this example, we can predict a cost, and there's a set of different costs which are all reasonable given the information that we have so far. Right. So for label 1, maybe we're pretty sure that the cost is going to be right about there. And for label 2, maybe we have a lot of uncertainty. Label 3, we have a lot of uncertainty. And label 4, we have a lot of uncertainty. And label 5, we have a lot of uncertainty. So let me describe what uncertainty means here a little bit more carefully. So I don't mean uncertainty in sort of a Bayesian posterior sense or something like that. What I mean is you have a set of predictors of the cost for each label. And as you get more and more information, you will throw away some of these predictors because you'll prove that they're wrong. And then you have a set of surviving predictors at any individual round. So you just ask your set of surviving predictors, what are the plausible costs for this class on this example? Okay, so there's a more complex but still efficient black boxable way to get at this. I don't want to go into detail about that, but you can actually estimate what are the plausible costs for an individual class label for any black box squared loss minimizing algorithm. Is a question?
So are these red uncertainties for a particular example?
Yes.
Or like over all?
For a particular example, you have a set of different regressors which predict the costs, and depending upon the example, those regressors have a range of possible costs that they predict.
Right. So it might happen for different example. We have like totally different
structure.
Yeah.
Okay, so the algorithm that we've been thinking about is one where you first take you first think about the smallest maximum cost. So there's class label 1 and class label 5 both have the small maximum cost. They have the smallest maximum cost. Okay, so that means that you're down to kind of 3 labels that you might worry about. One for 1, 3, and 5. But then there's another rule you can apply. You can say, oh, if the cost difference does not matter, as it does not for class label 1, you don't care about it. So maybe you only ask for the cost for label 3 and label 5. So we're calling this COLE, for cost overlap active learning. Okay, so this is the essential rule. For an individual example, you see what the smallest maximum cost is, and then you ask which labels have a minimum cost amongst the remaining set of regressors less than the smallest maximum cost. And then you ask which of those actually will get any information when you query. Okay, so you can prove this kind of works. There's some constraints, and I want to make sure that those are clear. So you need your cost predictors to factorize, so that's important. So you need to be able to kind of get a different regressor for each cost predictor that may or may not be removable. I don't know. You need to be able to do squared loss optimization efficiently, which is actually relatively straightforward. And we're also assuming that the world is kind of IID. So those are the constraints that we're working under. And then you can take something like, so this is the RCV1 V2, where this is, are you familiar with this data set? So
no.
RCV1 is, okay, it's an old NLP data set. There's a hierarchy over 104 or something like that classes.
Okay.
You use the cost as the hierarchy distance.
Mm-hmm.
And then you try to learn, right? And then you have some tests that you evaluate on. And now the funny thing is that you see very strongly here that we're actually doing better than the passive learner. Right, so the x-axis is the number of queries, the y-axis is the test error, and the passive learner queries everywhere and does relatively poorly. The active learner seems to do better with substantially less queries. So this is one of our data sets that we tried things on. Not all of them are quite as extreme as this, but it's still the case that often we actually do see the active learning algorithm perform better, which is not really predicted by the theory, but nevertheless kind of interesting empirically. Okay, so if we look at so think about the green line. So this is a parameter to the algorithm which has to do with kind of how aggressively you enforce bounds. So in the green line, we're not enforcing them very aggressively at all. It's the 10 to the minus 3. So there's a factor of 16 less queries, a factor of 16 less labels, and yet our performance is noticeably better in test time. All right, so that's it for active learning algorithms. So in general, I think the area of active learning is rather undeveloped in terms of both the empirics and the theory. And I expect to see quite a bit more developed because it's just constantly the case that you want to do some sort of active learning in practice. And okay, so there's two things. You want to do it in practice, and the second thing is that it's actually non-trivial in the sense that it can go quite wrong, as I was showing you way back here. Are there questions? Yeah?
So in this, like the streaming case, the simplest one, like we're getting unlabeled X and then we choose to get the label for it or not. And if we don't, then we don't use the unlabeled X information at all, right? So could we like use that information and have like a, I guess, semi-supervised?
Yeah,
active?
yeah, you could. I think that so supervised learning is kind of the base. That's where people know how to solve the problem well. Semi-supervised is kind of a twist on the base, and active learning is a twist. And the double twist is a little bit tricky because I think we don't really. I mean, we've made a good bit of progress in doing active learning. We see that there's some real promise in terms of the empirics that we observe, but it's not consistent enough, I think, yet. And I think making active learning work consistently and for a wide variety of supervised learning algorithms and efficiently is, I think we're not there yet in terms of active learning being the base. All right, so there's kind of a history of agnostic active learning here. And then there's another set of citations here. I'll put up the pointers to papers for the algorithms that I talked about. All right, thank you.